different kind of region and volume. And this is section 8. Let's see, which one is it? 8, 9. Volume using the disk method. And here's the type of problem that you're going to have. You're going to have a region just like we have in the past two, and it's going to be kind of wordy. So it's going to be all this stuff. The region enclosed by the function f of x equaling x to the 1/3. That's this curve right there. The horizontal line y equals 2. That's a horizontal line y equals 2, and the y-axis, which is that generates this green region. So it's really important to understand what the heck the green region is that you're working with. Find the volume of the solid when the region R, we'll call this the region R, is revolved about the line y equals 2. So we're going to spin it around this axis. Now, if I'm going to do my best to draw what that looks like, here's what I have is I'm going to have I got a y-axis, got an x-axis, and I got the line y equals 2. I got this curve that goes like this and then intersects at, looks like that intersection is 8. Here, this intersection is 8. So I'm using this region right here, and what I'm going to do with it is I'm actually going to rotate it around the line y equals 2. So what I'm going to do is I'm going to take this region and I'm going to spin it around this line. Okay, so I'm just going to take it and spin it around that line. And what it might create is kind of this this cone shape. It's a sort of a cone. It's not a cone because it's not a solid. It's not a line there. But in general, that shape would be something along this line, and that's the best I can do there. Where you got the center right here, and that center right there, that line that goes right down the center is that line y equals 2. So that's the shape that we have. One of the things that you'll notice that if you were to slice this, every slice on this cone represents a circle. Similar to what we did with the other ones, only you know that the area of the circle is pi times the radius squared. So if you take one of these and you kind of look at it and say, okay, well, let's take just that circle right there and let's extract that circle. It would look like this, where this radius right there, it would go from here to here. That value right there is the radius. That radius is defined by this distance from, if you can see the problem right underneath here, it's really defined as this distance right here, which is, we can calculate that distance by doing the top curve minus the bottom curve. So when we have this radius right here is the top curve minus the bottom curve. And it changes, right? I mean, it's going to change as you start to, the circle at the start is bigger than the circle at the bottom, but we're going to use the integral to help us do that. So what we're going to do to get the volume is we're going to do the volume of the integral from a to b of pi times the radius squared, and then we're going to write that radius in terms of x, which is right up here. So the volume of our thing is the integral from 0, that's where that region starts, all the way out to 8, and it's pi times that radius, which is 2 minus x to the 1/3, and we're going to square that. And that's going to be a calculator problem. Like writing it out is important, but then calculating it is another important thing. When I show the solution, what you'll see, and here's what we have right there. They pull the pi out in front. You can do that. It's a constant. But you can use this slider to kind of see how this thing is built. So as it's rotated and you build these disks that are on it, it generates this three-dimensional object because, again, when you integrate area, you should get volume. Hopefully that makes sense to you. If you need more examples, just let me know. I'll do another example for you, but I'm going to stop there for today in the video.